quiz. At the end of the semester here, we're going to drop a low homework quiz score. And I've actually set the computer up so that that's happened already. But I've also put in an assignment and a missing for that homework quiz that we're still going to take. So right now the drop is probably happening to your missing, unless you have another missing somewhere further back. So when we do that homework quiz and that gets graded and entered, you might see a little bit larger bump than usual. I'm going to drop a low homework score. We have one more homework check still to do for Chapter 6. I've put in the grade book, that last homework check, and marked it in as a missing for everybody, so that drop is probably happening for that missing. So when you turn that final assignment in, the drop will move to whatever your next lowest one, your new lowest one is now. And then the assessment period for this class is Thursday. In that assessment period, we'll have the option to take the Chapter 6 test. You're not required to do that, but if you're looking for another way to raise your grade, or that you want to do that, I'm going to present that as an option. If you'd like to do that, though, I'd like you to please email me by 8 a.m. on this Friday to let me know. And I've also doubled the high test score. So if you elect to do the Chapter 6 test and somehow that's your new high, obviously I'll update the doubled high test score, but I've done that already also in the grade book. So basically where it's at is if you do nothing else to finish the semester, your grade will not move because the drop's are already happening for the quiz and the next homework check, and you're not required to take the Chapter 6 test. So as you do these things, your grade can only get better, not worse. Well, unless you elect to take the Chapter 6 test and you have an oopsie and screw that thing all the heck up. But since you're given the option, I find that unlikely that you would elect to do that and then phone it in and do pretty poorly on it. And FYI, the last homework check is going to be Tuesday morning at 8 a.m. Since this class's last day is Monday of next week, it seemed to me to make more sense to just have one final homework check that wraps over, that Monday also. So Tuesday at 8 a.m. is going to be the final homework check rather than Sunday at midnight. We'll put that in there. Does anybody have any questions about any of those things?
Yeah.
Go ahead.
Will we be having a homework quiz on Chapter 6, or is the test the final test and quiz we're gonna have?
So the homework, there will be a homework quiz on Chapter 6 that everybody is going to take. I have put that assignment already in the grade book and marked everybody as a missing. So the drop that I'm doing for the homework quiz is being occupied by that missing. Okay. So when we take that, obviously the drop will move to whatever your low score would be after that.
Okay, thank you.
Yeah. So we'll do that at some point here in the next 3 class periods. We'll have our final homework quiz concerning topics from Chapter 6. Okay. Hopefully that feels pretty fair for those of you that are on, a grade borderline that want something, need something to kind of shoot for to help your grade out a little bit. I think there's a couple of options there to, make sure you do these last couple of assignments, and we're doing some things to help pad the grade a little bit. And you have that option of a 6th test to get in to, again, help your grade a little bit. So hopefully you guys feel that's pretty fair and generous. Yes.
So if we don't, no matter, if we want to take the test or if we don't want to take the test, either way, we have to email you by Friday?
No, just if you want to take it.
Okay.
So only if you are electing to do it do you need to let me know. If you don't want to do it, you don't have to do anything.
Okay.
And then that last assessment period then on Thursday next week, we'll just have a brief check-in for everybody, and if you're electing to do the test, you'll stay for that assessment period to do your test, and then you're free to go after that. But if you're not electing to do the test, we'll just do a final check-in, and you guys will be free to go to start preparing for whatever happens next, or whatever you have still left to do.
So you said even if we don't do anything, your grade will just be the same at the end of the year?
That's where it's set up now, yeah. If you elected not to do the homework quiz, which I don't know why you wouldn't, or elected to do none of the Chapter 6 homework, again, please do that. I know it's a stressful end of the year, and I'm trying to make the end of this class a little bit less stressful, knowing that, even if I can't get any of this stuff done, or if I make a big mess out of all of it, it's not like my grade's going to get worse at this point. So, again, the only way that it really could get worse is if you elect to take the Chapter 6 test and you do bad. Because whatever you do on the Chapter 6 test, I'm going to enter. But I find the likelihood of somebody electing to do that and then doing really poorly to be kind of slim, right? Hopefully you guys are aware and self-aware enough to know that, I don't know what's going on. I could take this and I kind of want to take this, but I shouldn't take this. You know what I mean? I feel like you guys are self-aware enough to know when that's going to be, if that would be a good idea or not for you. Okay? All right. So let's get going on Chapter 6 today. Chapter 6 is about more identities. So we have sum, difference, and multiple angle identities. And if you checked out the content library recently, you'll notice that I've put in a bunch of new stuff for Chapter 6. One of them is a new identity sheet that contains some of these. So those 3 Pythagorean cofunction and odd-even identities are old. And then we have some new identities for sum and difference and multiple angle identities. And we'll talk about those identities here today. So the first identity we're going to do, I'm going to derive kind of from first principles. This is not a process I'd expect for you guys to be able to repeat, but it is something that I expect that that you can follow the argument that we're making here. And then once we have that first identity, we can kind of use that to build out the other ones, so we don't have to do a time-consuming first principles derivation for any of the other ones. So that's what we're about to do. And what we're going to do is we're going to do the difference of 2 angles for cosine. So I'm going to start by just kind of drawing 2 angles on the unit circle. So this first angle, we'll draw, here. And we'll call this angle U. And then a second angle that we'll draw, say, here. And we'll call that angle V. And this distance between these two angles, I'm going to refer to as theta, which is u minus v. Okay. So if we embed a unit circle around this, I can't draw a circle very well, so I'm just going to not really put it in there. And look at the point that the angle u intersects the unit circle. We can call that point A, and the coordinate of that point then would be cosine u, comma sine u. If we do the same thing to this terminal side of angle V, I'll call that point B. And now I'm going to draw a second xy axis. And I'm just going to draw this angle theta here. Which I can do, right? I can just pick up and do like a translation and a rotation without changing the size of that angle theta. Still the exact same size. I've just picked it up and moved it to a new location so that it's now a standard position angle. If I do the same thing and look at the sides of the angle and where they're intersecting the unit circle, this side would be 1, 0, and this would be cosine theta, comma sine theta. And I guess we need to give these guys a name. I'm going to call this angle, or that point, A prime, and this point B prime. And what I'm going to do now is I'm going to basically make a triangle. So I'm going to draw a segment from A to B, and a segment from A prime to B prime. And that forms a triangle in each section. Now I know these two triangles are congruent by angle side angle, because I know that these side lengths are both 1, because they are radii on a unit circle. And I know that these angles are congruent because they're both size theta. So by angle side angle, or side angle side, excuse me, I know that these two triangles are congruent. So because I know then that corresponding parts of congruent triangles are congruent, I can say that segment AB is equal to segment A prime B prime. And this is the relationship that I'm going to use to kind of build out this new trig identity. So what I'm going to do is I'm going to write the length for this segment AB using the distance formula. So the distance formula would be the x-coordinate for B minus the x-coordinate for A squared plus the y-coordinate for B minus the y-coordinate for A squared, all square rooted. And similarly, the x-coordinate for B prime minus the x-coordinate for A prime squared plus the y-coordinate for B prime minus the y-coordinate for A prime squared, all square rooted. I'm then going to square both sides to get rid of those annoying square roots. And now I'm going to substitute in the actual x and y coordinates from these points. So for B, the coordinate was cosine V was the x coordinate, and for A it is cosine U. The y coordinate is sine V, and then sine U. Here, the x coordinate is for B prime is 1, and for the x coordinate for A prime is cosine theta, and the y coordinate for B prime is 0, and the y coordinate for A is sine theta. I'm just getting these from the diagram that we drew earlier, right? So I'm just filling in the corresponding x and y coordinates for the points A and B, and A prime and B prime. Now I'm going to expand all of these out, so I'm going to FOIL each one of these quantities out, well, except for this one, because it really doesn't need to be FOILed. And I'm just going to have to go down to a second line here to do that, but that's no big deal. And you might be saying, great googly moogly, this looks like a mess. And yeah, it got pretty big and messy here, but it's about to get a lot better. Because if we look, I see that I have a cosine squared v plus a sine squared v. So that just gives me 1. I notice I have a cosine squared u and a sine squared u. That's going to give me a 1. Now these two pieces I still have. Can't do anything with them right now, so I'm just going to recap. And if I look at the other side, I notice I have a sine squared theta and a cosine squared theta. So that's going to give me a 1. If I copy the rest of it in, which is a lot better, and about to get even better. So I notice that I have a 1 on both sides, so if I subtract 1 from both sides, those would cancel out. And I still have another 1, so if I subtract 1 from both sides, those would cancel out. And I notice everything here has a coefficient of -2, so if I divide both sides by -2, those will cancel out. And I'm left with is cosine v times cosine u plus sine v times sine u is equal to cosine theta. And if I recall, way back in the drawing that we made in the beginning, said that, we said that theta is u minus v. So this right here is an identity for the difference of two angles, for the cosine of the difference of two angles, I should say. Whew, that was a lot of work. Fortunately, we don't have to do it that way again. Now that we have one of these identities, we can use this to kind of build out the rest of them without having to go back to first principles and derive this geometrically. We can just kind of do some tricky algebra stuff. So the next identity that I'm going to look for is the cosine of u plus v. And the trick here is that I'm just going to think about this as the cosine of u minus a negative v. Since I've rewritten this as a difference of two angles, I can use the cosine of a difference of two angles identity that we just derived. So I'm going to get cosine of u times cosine of negative v. Oh my goodness. Those two shouldn't be in there. Yeeps! Make sure you guys caught that. That I erased those twos. That was a big mistake on my part. Sorry about that. Pretty bad when you screw up the writing down the identity itself, right? That makes a big mess. But I caught it in time for it to become a, you know, from a nuisance to a disaster, at least, right? And continuing on. So we have sine u sine negative v. And then we can use our cofunction, or our odd-even identities. So cosine of negative v is just cosine v. And sine of negative v is negative sine v. And so I can just move that negative sign out front and turn that into a subtraction. So there is my sum of two angles identity for cosine. And oftentimes, we like to combine these two into a single statement just for compactness. The way we usually write that is with plus and minuses. So the way we read that, if we want the sum of two angles, we're going to use the subtraction symbol. And if we want the cosine of the difference of two angles, we'll be using the addition symbol. So this is just combining those previous two identities into a single statement. This is the way it's written on the identity sheet that I put in the content library. And really the only reason we would do this is just for compactness sake, right? As mathematicians, we like to take up as little space as possible. Okay. All right, so one thing we can use these identities to do is they allow us to find the exact values of things that are not circle angles. So let's say we want to find the exact value of cosine of 75. Now 75 degrees is not a unit circle angle. But what I can do is I can take 75 and realize that that is the same thing as the sum of two unit circle angles, 45 and 30. And there's lots of possibilities here. You could have done differences as well. You could do like 135 minus 60 or something. Like that'll work as well. And there's lots of those. There's nothing magic about these two other than they give me 75. 75 is the cosine of 45 plus. And when I apply my sum of two angles identity for cosine, I get the following. And now everything is written as a unit circle value, or a unit circle angle, so I can go to my unit circle. So the cosine of 45 is root 2 over 2. The cosine of 30 is root 3 over 2. The sine of 45 is root 2 over 2. The sine of 30 is 1/2. So we have root 6 over 2 minus root 2 over 4, since they have a common denominator. And write it as root 6 minus root 2 all over 4. And regardless of kind of how you got to 75 degrees, as long as you use two unit circle values, this will all reduce down to that same expression. Okay. So let's now get the sum and difference identities for sine. So to do this, I'm going to say, okay, well, let's say that theta is equal to u plus v. So I know sine of u plus v is equal to sine theta. And if I use my cofunction identities from last chapter, I know that that's really equal to cosine of pi over 2 minus theta. And now it's tempting to want to think to use your difference of two angles for cosine identity right now, but we don't want to do that yet. What I want to do first is substitute v for theta, and then distribute that negative through. And what I want to do is think about this as my difference of two angles, where I've separated the u and v so that they're going to be in different expressions. So if I use my difference of two angles identity for cosine, I have cosine of pi over 2 minus u times cosine of v plus sine minus u times sine of v and then if I use my cofunction identity, here cosine of pi over 2 minus u is sine u, and sine of pi over 2 minus u is cosine u, and there is my sum of two angles identity for sine. Now I can just use that same trick that we did before and do u minus v as u plus a negative v and use the same identity to get my difference. I'm not going to actually write that down. I'm just going to write it real quick. Sines typically we condense these into a single expression. Okay. So, just like before, we can use this to find an exact value. So let's say we want to find the exact value of sine of 5 pi over 12. Well, usually easier to think about these in degrees. So let's just convert that into degrees. So 5 pi over 12 is actually 75 degrees. So I can think about this as 45 degrees plus 30 degrees. And then if I apply my identity for sine, we should probably leave everything in radians though, since the problem was in radians. So that's pi over 4 plus pi over 6. Sine of pi over 4 plus cosine pi over 4 times sine pi over 6. Sine is root 2 over 2. Cosine of pi over 6 is root 3 over 2. Cosine of pi over 2, or of pi over 4 is root 2 over 2. And sine of pi over 6 is 1/2. So here we have root 6 plus root 2 all over 4. Okay. We can get a sum or difference identity for tangent by just using the fact that tangent is sine over cosine. And if we do a little bit of cleanup, we would arrive at this. In the interest of time, I'm going to skip doing that because the algebra gets kind of hairy and I don't think it adds a lot of insight. So there's our angle sum and difference identity for tangents. So we have our identity for tangent, sum and difference of two angles. We have one for sine, sum and difference of two angles. And we have one for cosine, the sum and difference of two angles. So another thing that we can do here, we've used these identities to find exact values. We can also go the opposite direction and use these to come up with a single expression. So let's say we have something like this. So what you want to do is you want to think about like 47 as our u and 23 as our v. And if I go back and I look at my identities for sines, so I can just say that this is equal to sine of 47. Okay. These to do like verifying problems. So for example, say sine x minus pi is equal to negative sine x. So I would choose to work on the left-hand side here because I see that I could obviously use a two angles identity for sine. So I can say sine x times cosine of pi minus sine of x times sine of pi. Cosine of pi, if I go to the unit circle, is -1. And sine of pi, if I go to the unit circle, is 0. So that part just kind of drops out of there. And I'm left with -1 times sine x, which is negative sine x. And that's what I needed. That one was pretty straightforward. Let's do one that's a little bit trickier. Right, I have a cosine 3x on one side and a cosine 2x on the other. In general here, what I would do is I would choose to work on the one with the bigger coefficient, is usually the better idea. My sum of two angles identity for cosine. Oops. And I still have that cosine x over there. If I look, it's like, okay, I have one of those. I need to get a second one somehow. And I also have this echoing around and this extra thing. So here's the tricky piece, the thing that's not at all obvious at first glance until you've done a couple of these and seen that this is a trick you can use. I'm going to rewrite cosine x as a difference of two angles, because I know that's the only other way to get another cosine 2x there, is to somehow manipulate that piece. So when I apply my identity for the difference of two angles for cosine, I'm going to get cosine 2x times cosine x plus sine 2x sine x. And now I notice that these guys can cancel out because I have a negative sine 2x sine x and a positive sine 2x sine x. And then the other two are like terms, so they can add together. So I get 2 cosine 2x cosine x, which is what I needed. This trick here is not obvious until you've seen somebody kind of show it to you. So if you were thinking, boy, I would not have come up with that, don't feel bad, because that is not at all obvious of a trick to do. You have to be a little bit creative to come up with that idea. But now that you've seen it and know it's something you might need to do, it makes it much easier to come up with. Okay. Next up, we're going to talk about the double angle identities. And I'm just going to kind of mention how we could go about deriving these. So if I have a double angle, all I'm going to do is think about it as sine of like u plus u, and then I can just use my angle sum identity to derive this. I'm not going to do the derivation here in the interest of time. I'm just going to write them down for us. So sine 2u is pretty easy because it's just a single thing. Cosine 2u has 3 different representations. So it's sometimes a little bit tricky deciding which one you're going to want to use. But keep in mind that they're all equivalent, so it doesn't matter really which one you use. It'll just make things more or less convenient depending on your choice. So those are the double angle identities. And then the next ones that we'll talk about are the power reducing identities. And again, I'm going to write these down, but without the derivation in the interest of time. But I'll go here and point out really quickly. If I look at this identity, it's basically just a rearranged version of this, right? Where I subtracted 1 from both sides and then divided by a -2. Yeep! Good thing I went back and to talk about where that derivation was coming from, because I forgot the 2 there. Ugh. Okay. Similarly, we can do this and this. Okay. So let's do an example where we use one of these. So let's say we want to use the power reducing identities to find the exact value of cotangent squared of -165 degrees. So I'm going to start by rewriting this as using the reciprocal identity as 1 over tangent squared. And now I'm going to use the power reducing identity for tangent. Since it's 1 over, I'm going to be flipping because it's just the reciprocal. So I have 1 plus cosine of 2 times negative 165. And then 1 minus cosine of 2 times negative 160. And that's just negative 330. And with my odd-even identities, I know cosine of negative 330 is just cosine of 330. And if I go to my unit circle, I think that's root 3 over 2, but I don't want to make a mistake here. I've made enough of them already this morning, so let's just double check that real quick. 330 cosine is root 3 over 2. Right, so cosine of 330 is the x-coordinate there. Oops. Okay. Now, we don't like this as a final answer because we have fractions inside of fractions. So what I'm going to do is I'm just going to multiply the top and bottom by 2. It's going to distribute. So I have over 2 minus root 3. And we don't really like that as a final answer because we still have a square root in the denominator. To get rid of that, I can't just multiply the top and bottom by root 3 because it'll distribute to the 2 and then I'll have a root 3 stuck on the 2. So what I really want to do is I want to use the conjugate, which is the same thing as the original, but with the opposite sign in between. So I'm going to use the conjugate of the denominator. And then we just have to FOIL that all out. So when I do that, I get 5 plus 3 over negative 1. Or I can just write as negative 4 minus, or negative 5 minus 4 root 3. Oh my goodness, guys. Look what I did. Mr. Kulik, you're so is 4, you doofus. You know, sometimes we have ourselves one of those days. So that should be a 7. That should be a positive 1. So there. Oops. 7. That makes more sense. My apologies here, kiddos. And our last one is going to be a last example. So verify sine cubed of x is equal to 1/2 sine x times 1 minus cosine 2x. And we have a couple of options here. So you could attempt to work on the right-hand side and use the double angle identity. Or what I think is going to probably be easier is to work here on the left-hand side and use one of the power reducing identities. That's what I'm going to choose to do. But you could do the other and still end up with the right answer. So I'm going to start by rewriting sine cubed as sine x times sine squared x. Now that I have the sine squared, I can use my power reducing identity on sine squared to rewrite that as 1 minus cosine of 2x all over 2. And if I look, I have the sine, I have the 1 minus cosine 2x, and the 1/2 is really right here. So I can just take this out, and I have exactly what I need. That went pretty swimmingly. And we're going to stop here for today. So, with what we've done today, you guys should be able to do 1 through 20 and 35 to 40 from the homework set. And on worksheet 1, you should be able to do page 1 and page 2. We haven't talked about half-angle identities yet, so you probably wouldn't want to start page 3, but if you're feeling ambitious and wanted to read ahead, just to kind of get everything done, you're welcome to do that, but we'll be talking about those half-angle identities next time. So that's it for me for today. Are there any final questions before I dismiss you guys? Okay. Well, you are dismissed. Make sure you say bye into the chat. Have a good day. Good luck with trying this homework, and we'll see you guys again on Thursday. And we'll get a good finish this semester, right?